to the Highword Seminar. This is the GaNFast Demystified Your FAQ section being presented by Yiqi Zhang. My name is Fei Yang, and I will be the moderator for the section. All participants are muted for the section. Please use the chat function to ask a question and address it to everyone. We will be answering questions throughout the webinar in chat. Also, chat if you're having any problems hearing or seeing the presentation. With that, I will hand it off to Yiqi Zhang to get started.
Thank you, Fei, for the introduction. So in this section, I will be talking about some FAQs about GaNFast. Here's the agenda for today's presentation. First, I will be going over why is the integrated driver necessary for high-frequency design. And then second one is what's GaN's direct drive structure. So as you may know, there's a very common structure of cascode, and I will be going over some of the advantage of direct drive versus cascode structure. Third one is, does GaN have a body diode? As you may know, GaN has a different structure than a traditional MOSFET, and I will be answering questions of how does GaN conduct in the reverse direction, which will bring me to the third quadrant conduction introduction for GaN. And then the next one is how to minimize GaN's third quadrant conduction losses. With the different conduction structure of the GaN, I will be going over how to minimize that loss. Next one is how can integrated smart feature and protection in GaN simplify design and enhance robustness. So TI-GaN has integrated a lot of smart features and protection, and I will be going over some of those features to see how that can help with your design. Next one is what are GaNFast package variants and cooling strategies. So in this one, I will be going over the bottom and top side cooled variation we have and how to choose a thermal design based on type of package you choose. And lastly, there's a perception of that GaNFast is much more expensive than silicon MOSFET. So I will actually go into demystify that and tell you about how GaN can actually reduce the overall system cost. First one, I will be going over why is integrated driver necessary for high frequency design. On the left, you can see it's a very typical traditional standalone GaNFET plus external gate driver. So there are a lot of parasitic inductance included in this structure. So from 1 to 6, there are some parasitic inductance in the driver. There are parasitic inductance in the GaNFET. And also there are some parasitic inductance on the PCB traces labeled from 1 through 6 here. And all the 6 inductance are included in the gate drive loop inductance. And also number 4 here is a common source inductance, which I will be talking about what are the effects of this parasitic inductance in the next few slides. So first is looking at the common source inductance that's in the red circle down here. So common source inductance actually reduces the DIDT during turn on and turn off. So because of the slower DIDT caused by the common source inductance, it will increase the power dissipated during the DIDT ramp. So on the right, you can see it's a simulation plot. And the blue line is with 5 nanohenry of common source inductance, and the red one is with 0 nanohenry of common source inductance. And you can see the 5 nanohenry common source inductance actually increases the turn-on loss by 60%. So it has a very significant effect on the switching losses. And next one is the gate loop inductance. So all the previous labels through 1 through 6, those are included in the gate loop inductance. So firstly, it limits the ability to hold off the GaN device during the VDS ramp, and there are chances of shoot through, and that can cause the power increase the power dissipation, and also it can cause the failure due to SOA issue. So on the right, you can see it's a simulation plot with 10 nanohenry of gate loop inductance. It can actually cause shoot through. And another thing is even the gate loop inductance will increase the ringing. So it will have higher stress on the gate, and ringing can cause the device to unintentionally to turn on or turn off. And you will need loop resistance to is required to damp the ringing. So there are a lot of negative effects on the switching losses and also reliability issues caused by the gate loop inductance. So looking here is TI's approach to the GaN device, which we integrated a driver with our GaN device inside a single power stage. So with here, you have the lowest parasitic inductance. You only have a little inductance inside the package from driver to the GaN FETs and some bond wire inductance. So the integrated driver actually eliminates the common source inductance and significantly reduces the inductance of the driver output and the GaN FETs. So it gives you the minimum parasitic inductance. And we do have app notes of optimizing GaN performance with the integrated driver that outlines how the integrated driver can help with both reliability and switching losses for GaN FETs. And then the next one will be, I will be talking about what's GaN's direct drive structure. So as you may know, there's a very common structure in the market called cascode, as you can see on the left figure. So cascode is where you have gate of the GaN connected to the source of the MOSFET, and then the MOSFET gate is driven by a gate driver. So in this way, whenever you try to switch a device, you're actually switching the MOSFET on and off, and then you will be experiencing the reverse recovery loss from the MOSFET, switching loss from the MOSFET, and also slew rate in this case cannot be adjusted. So actually TI's approach to the GaN device is what we call a direct drive. So where the gate of the GaN is driven directly by the gate driver, and MOSFET is always on when VDD is greater than UVO. So whenever you have bias supply to our device, then the MOSFET will be always on state, and then we drive the GaN device directly on and off. So some of the advantage of the direct drive structure is it doesn't have the reverse recovery from the switching MOSFET. So you have absolutely zero reverse recovery with direct drive. And you will have the benefit of the low gate charge of the GaN FET. You don't need to worry about the MOSFET switching on and off. And also you don't have the low voltage MOSFET switching losses. With our integrated driver, we're able to implement a programmable DVDT. So with the external resistor value, you can actually adjust your DVDT value all the way from 20 volts per nanosecond to 150 volts per nanosecond. So you can fine tune your slew rates based on your application to optimize the EMI versus efficiency. One other benefit is MOSFET can be used as a current sensor. So we can implement some of the protection functions such as overcurrent protection in our power stage. I will be talking about some of the protection and smart features we have in the next few slides. And also we have app notes about direct drive configuration for our GaN devices. Now, next question is, does GaN have a body diode? So GaN has a different structure than a traditional MOSFET. So traditional MOSFET has a body diode that's kind of like in parallel with the MOSFET, but GaN FET actually doesn't have a body diode. However, it's capable of reverse conduction even without the body diode. So if you look at the figure down below here, this shows two different conduction modes of GaN device. So whenever you have VGS greater than threshold voltage, then the current will be flowing in the forward direction. And whenever the VGD is greater than VTH, then the current will be conducting in the reverse direction. So the symmetry of the device helps conduct in the third quadrant with diode-like behavior, even in the off state. And also, like I mentioned previously, unlike cascode, the silicon FET is always on. And then in this case, you don't have any reverse recovery time or reverse recovery losses, QRR, with GaN third quadrant conduction. On the right is some more more intuitive way of seeing how GAN can conduct in the reverse direction. So whenever you have VGS greater than VTH, then it's just going to be a straight line conducting in the forward direction. And whenever the VDS is less than VGS minus VTH, then this will be the region that you will be conducting in the reverse direction. And this value VGS minus VTH actually defines what's the reverse voltage drop for GAN conducting in the reverse direction. For our TI GAN device, we have around 5 volts of reverse voltage drop. And this actually is larger than what you see in the typical, MOSFET body diode conduction. And in the next slide, I will be going over what are techniques trying to minimize the losses during that time resulted by this 5 volts voltage drop in reverse conduction mode. Here is a simple formula you can use to estimate what's going to be the reverse voltage drop based on the current value you are conducting in the reverse direction. And also, we do have app notes talking about that can have a body diode and understanding the third quadrant operation of the GAN on our website. So next one is, does GAN have a body diode? Here are some recommendations that we are giving to the customer about using our GAN in application. So it's recommended not to add the anti-parallel diode with the GAN FET to conduct the reverse current, because adding the anti-parallel diode will add the additional output capacitance to the switch node and increase the switching losses. So what we suggest, for example, this is a totem pole PFC with GAN using GAN device, and then you can just use GAN to conduct either forward or reverse direction current without using an anti-parallel diode. And then there are 2 ways of minimizing the third quadrant conduction loss. First way is to use adaptive dead time that's implemented by the controller. So for example, in the totem pole PFC, in a different time in the AC cycle, you can have different dead time based on the AC current you're looking at the moment. And this is a very common way. However, our TI GAN has a unique feature called ideal diode mode, which is similar to the adaptive dead time, but it's implemented in our GAN device itself. So you don't need to do extra controller manipulation to implement this feature. I will be going over the ideal diode mode feature in the next slide. So this is a quick introduction of the ideal diode mode. So it's triggered by the detection of the negative VDS and when input signal is low. So whenever it sends the reverse voltage drop, and then you will be triggering the ideal diode mode. And then it will be turning on the GAN FET within 35 nanoseconds whenever the reverse voltage is detected. So it significantly reduces the amount of dead time you might implement in your system to reduce the amount of third quadrant losses. And then there's a built-in blanking time to prevent shoot-through whenever you have asynchronous FET turned off. And then it saves designers' effort to fine-tune the dead time. And we do have app notes talking about ideal diode mode in detail outlined here. In next slide, I will be going over a boost converter example, as you can see on the right, and how it can save the synchronous FET third quadrant conduction, which is a high side FET. Okay, so this one I will be quickly going over a cycle of a boost converter configuration to see how that can help with your third quadrant losses. So on the right, I have several waveforms. Top one is the low side FET input signal. Next one is high side FET input signal. Next one is low side gate signal, high side, and then it's high side gate signal. So both gate signals are inside the FET, and the input signal are the one we feed into the power stage. And last one, we have a switch node waveform. So looking at the first state, whenever you have an in-pin low via, whenever you have the input pin low and then that will drive the gate low, which means that the switch node will be starting ramping up in this stage. And then next one is whenever the COSS is completely discharged, and then it will start to entering the third quadrant conduction, and then you will see the 5 volts voltage drop I've been mentioning before over here. So it's slightly above the bus voltage in this stage. And then next one is whenever if you are using our FET with synchronous FET mode, which is ideal diode mode, then after a 35 nanoseconds detection time, and then our FET will be turning on even before the input signal is received. So as you can see, the input signal is still low in this case, but the gate signal is already going high, which means the FET is turned on to minimize your dead time loss in this case. And then you can see the switch node actually goes down because it's in the FET is in the on state in this case. And then the next one is when the input signal is received, and then nothing happens because the FET is already in the on state at that moment. The next section is whenever you are conducting in the reverse direction with FET turned on already. So it's just normal conduction. And then the next section is whenever you have in pin goes low to turn off the FET. And this one, you see the gate and in pin is synchronous. And whenever you have the in pin to command it going low, and then the gate will be shut off. And then you will enter the second third quadrant conduction of the synchronous FET. And over here, you will have the FET off via in pin low. So this is second third quadrant conduction in this cycle. And we do have a third quadrant blanking time implemented. So it's to prevent that the synchronous FET be turned on again during this period to prevent any shoot-through events. And lastly, you will have FET off via in pin low in this case. So this just quickly walk you through how the ideal diode mode work in a boost converter. And we do have more detailed explanation in the app notes mentioned in the previous slide. Okay, and the next topic is what are the integrated smart features for TI GaN? First one is adjustable turn-on slew rate. So a common question asked by the customer is that we have integrated driver, so how do we adjust the slew rate based on our application? So firstly, we do have give users external resistor value to adjust our internal turn-on slew rate. So as you can see in the bottom, we have 2 waveforms. One is our device tuned at 150 volts per nanosecond. This is a maximum slew rate where you can actually save your switching losses by going with very high slew rate. And on our right is a waveform with only 20 volts per nanosecond slew rate. So this is a very low slew rate where you don't see any of the overshoot or ringing. So this is best for EMI and ringing performance. So you can adjust the value anywhere between 20 volts per nanosecond to 150 volts per nanosecond, and it helps you to balance between the switching losses and ringing, and it can be fine-tuned for EMI in your application. And then the next feature is what we call the overcurrent protection and short circuit protection. That's integrated in our GaN FET. So you don't need to externally implement these 2 features. So overcurrent and short circuit protection, those are differentiated by the DIDT. So whenever you have slower DIDT, it will be seen as overcurrent protection, and it will be triggered with cycle by cycle operation, which means that in each cycle, you will try to start itself and see if it's still in the overcurrent state. If it is, then it will be shut off in each cycle. And if you have very high slew rate, very high DIDT caused by a short circuit, then our device will be entered a latched off condition where you have to hold the in pin low for 350 nanoseconds to reset reset the fault signal, or you can power cycle the device. And also the overcurrent and short circuit protection has different thresholds for different RDS on device, as you can see in this table. I will be going over some details of the overcurrent and short circuit protection we have in next few slides. So this one is a cycle-by-cycle overcurrent protection waveform that's captured in the lab bench. As you can see, whenever you have a slower DIDT, in this case it's 20 amp per division, it's rising up relatively slowly, 10 amp per microsecond, and then you will be triggering the overcurrent protection. In this case, you can see in every cycle, the device will try to start itself, and then whenever it sees it's overcurrent, then it will be shut off again. So it's a cycle-by-cycle operation, as you can see in this waveform. And also, we have short circuit protection. So whenever you have a short circuit event, then the DIDT over here is going to be much faster. Over here, you have 718 amps per microsecond slew rate in a short circuit event. And in this case, you can see the GaN FET will be shut off. It's in a latched off condition. And then you will have to manually reset the device by holding the in-pin low for X amount of time for our device. And also for the short circuit protection, we do have stop turn off action. So over here, you can see the switch node ramp up and without too much overshoot in this case. So it can protect our device to be within the safety operation area. And this waveform shows how you can manually reset our device without power cycling. So you can actually reset the device by holding the in-pin low for over 350 nanoseconds. So in this case, it's around 394 microseconds before the fault is reset in this case. So blue line is actually the inverse of the low side PWM input. So it has a very short, on the left, you can see it has a very short going high period that's caused the shoot through case. And then after that, it's hold low. So after 394 microseconds, the fault is reset in this case. One additional smart feature we have is the digital temperature output signal. From this pin, you can see what are the real-time die temperature in this case. You will be outputting a digital PWM signal with a fixed frequency, 11 kilohertz, and the duty cycle will be varying from 3% to 80% based on what are the real-time die temperature all the way from 25 degrees C to 150 degrees C. So based on the temperature output, you can see how to adjust your control to your system. And on the bottom, you can see it's a fault output table. We do have two individual pins. One is called fault pin, and one is called OC pin. So based on the status of these two pins, you can know if the device is in normal operation, if it's in UVOO or over temperature, if it's in over current or short circuit condition. So you can know exactly what the device is behaving in this case. All right, next topic I will be talking about what are GaN FET package variants and cooling strategies. So right now we have two generations of device. First generation device we have is 8 by 8 millimeter QFN package, bottom side cooled. It's targeting at power level under 2.1 kilowatts. It has 50, 70, and 150 milliohm configuration. And just recently, last November, we launched our second generation device, which is targeting at larger power level and with larger thermal capability. So it's in a larger package, 12 by 12 QFN. This one you see here is a bottom side cool device. It's with larger thermal pad, so it's capable of going up to 4 kilowatts in this case. And additionally, we do have an automotive qualified part that's G35 2X. It's capable of going at a slightly higher voltage as well. It's at 650 volts voltage capability, and it's topside cool device. So because it's topside cool, it can be attached to a cold plate, which gives it a much higher thermal capability. So this one you see it's capable of going to 6 kilowatts. And you can ask for samples using this tooling, and our first generation device is already in mass production. In next few slides, I will be comparing some difference between the top side cooled versus bottom side cooled device, and what are some cooling strategies with these two devices. So this one you can see is a comparison between a bottom side cooled versus top side cooled device. So actually the thermal, if both the thermal pad size is directly related to your thermal capability. So for our bottom side cooled device, we have 79 millimeter squared of exposed pad size. And for our top side cooled device, we have 63 millimeter square exposed pad size. So this is a example of bottom side cooled device with heatsink configuration. So this one, the heat will go through the thermal pad at the bottom and then go through the PCB, go through the thermal interface material, which is tin, and then go through the heatsink. And the heat is dissipated by using thermal vias. As you can see in the bottom figure, there are a lot of thermal vias we put in our evaluation module, trying to dissipate the heat from the bottom of the PCB. So here's a calculation example of how you can estimate how much loss you can have with this bottom side cooled device. So assuming you have 55 degrees C ambient, 125 degrees C maximum junction temperature limitation for your application. And then we're estimating 4 degrees C per watt junction to ambient thermal impedance, assuming there's 1.8 degrees C per watt for the heatsink. So allowed loss is just the thermal difference between the maximum junction temperature minus the ambient temperature divided by the thermal impedance. And in this case, the allowed loss for this bottom side cooled device is 17.5 watts. And in the next few slides, I will be going over some example calculation for the top side cooled device. We do have application notes that's for a bottom side cooled device for QFN 12x12 package that's available online. You can check our thermal performance and some of the the thermal recommendations. For example, here we have a thermal interface material example here. Now moving on to the top side cooled device. So there are two very common ways of dissipating the heat for the top side cooled device. One is with the heatsink from the top side, and then the other one is with the cold plate. So if you are using heatsink for the top side cooling device, there are normally two ways. One way is to use one heatsink to cover multiple devices with thermal interface material, as you can see on the top figure. And then there's another way of using individual heatsink with solder, as you can see in the bottom. So with the individual heatsink, actually you can further reduce it because you're not counting the thermal impedance from the thermal interface material. And then on the right, there's a way of cooling the device using the cold plate. So actually, in this case, you're eliminating the thermal impedance of the heatsink as well. So there are three common ways of attaching the device to the cold plate. One is using gap filler gel, and second one is using gap filler pad, and third one is using the ceramic substrate with thermal grease. Which I will talk about some of the advantage and disadvantage for these three materials in later slides. So here are two calculation examples with heatsink and with cold plate. So for the top side cooled device with the heatsink, because it doesn't need to dissipate the heat through the PCB, so it doesn't have the PCB thermal resistance as you're seeing in the bottom side cooled device. So with the same example of 55 degrees C ambient and 125 degrees C maximum junction temperature, actually we can use a slightly smaller junction to heatsink thermal impedance, and that helps you to increase the amount of loss dissipation from 17.5 to 21.9 watts with top side cooling devices with heatsink. And if you want to further reduce it, if you want to further reduce the thermal impedance, you can use the cold plate variation. And in this case, you don't even have the thermal impedance with the heat sink. And then for in the same example, 2 degrees C per watt junction to cold thermal impedance can give you a allowed loss of 35 watts. So that dramatically helps with your thermal capability with the topside cool device. And we do have some examples of thermal interface material you can use over here. And here I will quickly go over some of the advantage and disadvantage of each thermal solution with topside cooling device with the cold plate. So for the gap filler gel, it's excellent conformability and good tolerance in component height variance and thermal planarity. And then the disadvantage is it has a relatively high thermal impedance with gap filler gel. Moving on to the gap filler pad, it has the lower thermal impedance compared to a gel. However, the disadvantage is it will have extra pressure applied on the package or solder joint. And third one is a ceramic substrate with thermal grade. It has the best thermal performance. However, it has a higher cost and it has the same problem of extra pressure applied on the package or solder joint. So based on your application and cost solution, you can choose different thermal solutions to your topside cooling device with cold plate. Now, the last question I will be going over is how can GaN reduce the overall system cost? So there's a perception that GaN is much more expensive than the silicon MOSFET. How much will it be? How much more expensive it will be when I implement the GaN in my solution? So this is a comparison of 2 different topology. One is super junction MOSFET-based dual boost PSC, and one is GaN-based totem pole PSC. So in this case, actually, GaN is a new topology enabler. In this case, GaN is really suitable for this totem pole PSC topology because super junction MOSFET has large reverse recovery loss, which can increase your shoot-through risk due to insufficient dead time. And like I mentioned before, GaN FET with zero QR, zero reverse recovery loss is ideal for this totem pole PSC in a half bridge configuration. So with this new topology, actually, you can reduce the amount of components used in this topology, as you can see in the bottom table. So if you compare the efficiency, the totem pole PSC with GaN actually can help you to go from 98% to 98.8%. And also you can achieve power stage cost parity with super junction MOSFET, even with the GaN-based totem pole PSC because of the less components used in this topology while you're increasing your system efficiency here. And also, because GaN can switch really fast with very fast slew rate, actually it can help with your efficiency and reduce your switching losses. And by this way, GaN can reduce the system level cost by going to higher switching frequency. So it can in turn reduce the size and cost of magnetics. In the bottom, you can see it's the 2 comparison of transformer and then a choke, an inductor for the PFC. So on the left, you can see it's a comparison of 100 kilohertz transformer versus 1 megahertz transformer. And you can see the size is dramatically smaller and the cost is in turn less expensive for the higher switching frequency transformer. And then for the inductor size, it's a 40 kilohertz versus 100 kilohertz. So you can see a 3.2 times reduction in the inductor volume. So it helps with your power density, and also it can help you to reduce your system cost. So that answers the question of how GaN can reduce your overall system cost. So that brings me to the end of the presentation. Thank you so much for your attention. And then in the slides, be sure later you can find all the app notes that's attached in the link. And then at this moment, I will be answering some questions from the chat. Thank you.
Thank you, Yiqi. And we do have some questions from the audience. So the first question that we received is, what are the pin connection for the exposed pad? Is it the same for the top cool and bottom cool devices?
Yes, so it's a very good question. So the exposed pad is connected to the source of the GaN FET. So whenever you are considering your thermal solution, for example, let me bring up my slides again. So it's all connected to the source of the pad, so you don't want to accidentally short true FET. So for example, in this case, you will have to apply a thermal interface material for the, the insulation purposes, and then you can attach heatsink. And then in this case, on the bottom, you can have individual heatsink, where then you don't need to have the thermal interface material for the insulation, and then you can directly attach individual heatsink to the thermal pad.
All right, thank you, Ichi. And we do have some other questions. And for people who are joining late, feel free to send your questions in the chat window here. So the second question is actually regarding the university program here. The question is, will this GaN FET sample be available for the university program? And would that be available for students to work on?
Yes, of course. So we do have a lot of engagement with a lot of universities. So if you are university students who are trying to evaluate our GaN, you can always try the samples.ti.com to request samples, or you can reach out to our sales and marketing team, and we can definitely send you samples of ICs or evaluation board for your research.
Great. So the next question is, regarding the DVD control, can this storage be done dynamically depending on operating conditions?
So right now it's a fixed DVDT that's set by an external resistor value. You can use a potentiometer trying to adjust the DVDT, but at this moment I would suggest you to stay with a fixed DVDT for a more reliable operation at this moment. So short answer is please stay with a fixed DVDT at this moment for a more reliable slew rate in this stage.
Thank you, Ichi. And the following question is, where do you see the applications, requiring the 2 to 4 kilowatt power?
So in this power range, actually, some of the end application we've seen very commonly is in server, telecom, power supply space, and also some power supply for the gaming space. So a lot of customers are trying to implement, PFC plus LLC or some other DC-DC topology, such as phase shift full bridge in the 2 to 4 kilowatts power. So GaN is a topology enabler for the totem pole PFC, and this is a very exciting new topology that customers are trying out compared to the traditional, diode bridge or dual boost PFC. And they've seen a lot of performance improvements, such as efficiency boost, and also they can save on the system cost by having smaller magnetic sizes. So yeah, definitely that's a big space we've seen people are using in the 2 to 4 kilowatts power space.
Sure. So I do see some questions, regarding the ideal depth mode. So let me try to combine them and ask them together to you. So basically the question is regarding the ideal depth mode. How would you be able to verify, it is achieving ideal depth mode, and how do you verify the data it is adaptively adjusted during your design stage here?
Okay, yeah, that's a very good question. So in our app notes, we actually have some test waveform you can try to look at. So in the test waveform, in the test we did, actually we have a fixed very long, just intentionally have very long dead time implemented in the converter. And then we just observe the switch node So in the switch node, actually, you can see from the extra third quadrant, you can see the voltage rise of the 5 volts, like in the waveform before. So you can see what are the actual dead time compared to the dead time you set. So with the ideal diode mode, you can see actually the third quadrant conduction is always around 35 nanoseconds, no matter how long you set your dead time to be from the external controller. So by setting an external controller to output very long dead time, you can verify that our ideal diode mode is actually working in this case. And I think there's another part of the question. I don't remember. Can you repeat the other part of the question? Or did I answer the question already?
Yeah, I believe you already answered all the questions regarding the ideal diode mode. And the next question is regarding the layout here. So are there any precautions that needs to be observed, for the VDD power supply routing and decoupling?
Yes, sure. So as far as the layout, actually, we do have layout guidelines that we're going to be putting on the web soon. So in the high frequency design, it's very important that you have optimized power loop in this case. So for example, the decoupling capacitor you mentioned before, it has to be stay very close in the power loop. And then it's very important that you have a power loop return right underneath the device to maximize your inductance cancellation to minimize the power loop inductance. So power loop inductance will cause a lot of issues such as ringing and voltage overshoot in a very high slew rate application. So it's very crucial to have an optimized layout for the GaN device. So yeah, please check back on ti.com/GaN for more information about layout in the future. We will be posting a lot of materials in the near future. So yeah, please go and take a look.
Thank you, Yiqi. And we also we do see some questions regarding on voltage level of the GaN devices. Basically, the question is, what are the voltage level of the GaN devices, and can it be applied to higher bus voltages? And the follow-up question is, regarding on the gate driver, how is the gate isolation be applied?
Okay. So first is the voltage level. So our first generation device and some the bottom side cooled second generation device has 600 volts maximum voltage rating. And then for our top side cooled, the automotive qualified device, we have 650 volts maximum voltage rating. However, in the real application, we do recommend that you go slower to leave some margin for some transient response. So for the 600 volts device, probably you can operate the bus voltage under 480 volts, and for the 650 volts device, you can have a bus voltage under 520 volts. And regarding the isolator, we do recommend a couple isolators to pair with our device. It's the ISO 77 series that gives you a very good transient immunity at very high slew rate, 100 volts per nanosecond in this case. And then, yeah, that's something we use on our reference design and our evaluation modules.
Sure. And the follow-up question is, regarding on the switching frequency, what is the maximum switching frequency for TI GaN?
Okay. Yeah. So first, for the first generation device, we have up to 1 megahertz switching frequency, and for our second generation device, it's capable of going up to 2.2 megahertz switching frequency. So here's the maximum drivability from our GaN driver perspective. However, another very important factor you need to consider in your application is your thermal design. So by going over to much higher switching frequency, you will experiencing higher power losses from the GaN FET. And in this case, the limiting factor is not only the driver of our GaN device, but also how you implement your thermal design. So if it's a hard switch application, then the thermal will be definitely be a constraint in the application. So yeah.
All right, thank you, Yiqi. And the other question is actually regarding on the packaging, on the thermal interface material. So basically the question is if you're using some thermal grease, or other thin materials, do you need to apply pressure on the contacts?
Yeah, so there's always gonna be some pressure applied, and then regarding the assembly, I think it's recommended to go through the app notes we have for the topside device. I think it will be released in a couple in very shortly, and then we will go through the assembly methods for different thermal interface materials. Different thermal solutions for the topside cool device.
Thank you. And the last question probably is regarding the isolated gate driver. The question is there any plan to replace the isolated gate driver in LMG34 series to improve the noise immunity?
Yeah, so that's probably a question for the isolator group. So I think they do have roadmap plans for isolator with higher voltage immunity, higher CMTI rating. But yeah, currently probably it's a better question to ask for reach out to the isolator group, sales and marketing for if they have any future plans.
Okay, great. I think we are right on time for this section here. So thanks, Ichi-Jung, and thank you everyone for joining us. So all the section recordings and presentations will be available to view later this week on ti.com/high voltage seminar. You will also receive an email with links to the on-demand presentation and a post-event survey. We would like your feedback so we can continue to improve our content for future seminars. Thank you again and have a great rest of your day.